starting to talk about discrete time systems as opposed to signals last time. And we started talking about different ways that we describe discrete time systems and how they operate. We'll do that today. Talk about different system descriptions, which lead us then to different techniques that we have for system analysis, which is what most of the course is actually about. And so this will give us some context, but before we dive into all the different techniques, we've got to first tackle one topic that we'll do today, which is system classification, where we tell from the system description whether or not the system fits in the right kind of category so that it's compatible with the system analysis techniques we're going to come up with. Because if it's not compatible, if it doesn't have all the right properties, then on which our system analysis techniques are based, we're going to, if we try to apply them, we're going to get erroneous results and mislead ourselves. So, last time we got through speaking about a couple different ways we could describe the operation of a discrete time system. We started with sort of a verbal description of the behavior that we wanted, and then we translated that in the case of a two-sample averager. We described then how that system would respond. So the system response inputs was one way that we describe the behavior of a system. It's a signal, and out came a certain other signal, and ultimately, in order to understand how a system works, if we put in lots of different inputs, watch what did in the output, maybe over time we could it's not intuitive. So we'd like to make that a little bit more disciplined process. So we'd like to refine that a bit and come up with some particular inputs that we can find the response to that give rise to some system analysis technique. And we are going to do that. We'll move that to the unit sample response. That'll be our kind of standard input. And that will give rise to the method of convolution for how we can do system analysis. That input can give you the out and find out what the output is that I can describe. If we choose this very carefully, we can take the response of the system to that particular input and then generalize it to find the output for any signal. Moved on to our second mathematical kind of description of a system, where we wrote an equation. And a particular kind of equation, we called it a difference equation. Which described the current output, the output at any instant time, n, and the index, in terms of the current input, x of n, maybe some previous inputs, could be also previous outputs, could be future inputs, but in terms of other data points, but an equation that relates the input to the output. So it's input to output again, but in the forms of an equation. And once we have that kind of description, well, how are we going to use that in system analysis? Well, we're going to end up solving that difference equation. Determine the output for a particular input. So you got to give me an equation, you got to give me the input signal, and maybe you need to give me some initial conditions. And by going through the process of solving that difference equation, similar to how we solve differential equations in 228, we can determine what the output's going to be. Turns out I could also find the output given this equation. If I don't need a closed form solution, this would give me an analytical solution. Equation of sorts. I could get sample values very easily using the difference equation, using the method called recursion. And we'll demonstrate that today. where we literally implement the difference equation and take our sample values, our number values, and crunch through the mathematics, just like a computer would do, or some digital hardware would do, anyway. And then we took that difference equation and we translated it into a block diagram. And it turns out all we needed were three particular components to draw to implement a standard difference equation. We needed things that had gain, we needed things that added, we need things that delayed. Question?
What does it say under analytical on the board?
It says sample values, and then that leads to recursion. So we took this actual difference equation, we said, well, okay, if I take my x of n in and I multiply by half, and then I need a delayed version of x of n, so I'll run it through a delay block. Now comes x of n minus 1, and I just scale that by a factor of 1/2, so I'll run it through a gain of 1/2, and then add those two together, so I get a summing stage. And with just these three blocks, with multipliers, adders, and delays, I can create a difference equation. And those are the only building blocks I need. And you could conceive these could be blocks of digital hardware. You probably studied in 133 or 233 how to make a digital adder. And you can gang together adders to make multipliers of digital numbers. And delays are simply, well, they're simply memory units or shift registers. Take a sample in, wait till the next clock cycle, and shift it back out. So basically, with some memory and some combinational logic, you can make any difference equation implementation. So this gives us some insight into a hardware implementation. So this is more around implementation. And it's kind of interchangeable with the difference equation. It's just a different way of depicting the difference equation. So we don't get a new analytical technique to go along with block diagrams. Now, that's as far as we got last time. Before we leave that, it works both ways. We should be able to see a difference equation and draw a block diagram implementation. So if you were given this as the block diagram implementing a digital system, kind of trace that through and figure out what the equation of the output, y of n, in terms of x of n and its delays, and maybe y of n and y its delays. And again, as we did in the forward case, it's best to kind of start here and start naming these signals. So if we have x of n coming in here, you get 3x of n coming out. If we have x of n coming in here, and then the delayed version is x of n minus 1. So see if you can trace through that diagram and come up with the difference equation, y of n equals something, this particular implementation. Let's see, we've got 3x of n here, we've got x of n minus 1 in there, 2x of n minus 1 coming out there, add together, and when y of n comes in here, what comes out of that delay line? Y of n minus 1. We multiply by minus a quarter, and so then that gets added in. So this would be the difference equation that this system was implementing. Questions on that? Either way, that makes sense. So we should be able to go kind of both ways. Given a difference equation, you can draw a block diagram. Given a block diagram, cover the difference equation. They are interchangeable. Okay. For most systems that we're going to talk about, we can write a difference equation in a standard form. Draw a block diagram in a generic form that would fit pretty much any system that we're going to be dealing with our analytical techniques. It puts a little bit of constraint on the particular classes of systems we can work with, and we'll come back and address that after we identify what those classifications are. But if we've written a difference equation as y of n, the current output in terms of x of n, maybe with some gain, maybe some delayed versions of x of n multiplied by other gains. And as we saw in that last example, if there's some y terms that are fed back in, we could always write it out in this form, where, again, we use the same kind of convention we did in 228. All of the x terms have numeric coefficients in front of them, we call b coefficients. All the y terms have a coefficients. Subscripts, well, back in 228, the subscripts went with the derivative orders. Here in discrete-time systems, the subscripts go with the delay orders. So x of n minus 1 gets the b1 coefficient. X of n minus 2 gets the b2 coefficient. Similarly, y of n minus 2 gets the a2 coefficient. And it's always written in terms of current output without any gain in front of it, so that what would be the a0 coefficient is usually normalized to 1. And if you want to kind of relate this back to the way the standard form we use in 228, you can bring all these a terms over to the other side, have all the y terms on one side, all the x terms on the other side, which would also be a comparable standard form. I tend to write it this way because this very explicitly tells us how to compute the next output. This is an implementable equation that we could actually put into a computer, have it do it for us, and it would be implementing our particular system. So everybody okay with the structure on that equation? If that's our structure, then using those same block diagram forms, I've got all these x of n's and delayed versions of those. So I can stack up a bunch of delay units where I get x of n minus 1 and then take it and delay it again and get x of n minus 2 and keep delaying for however many terms I need. And each of those then go through a multiplier that scales by the b coefficient. And if we have y terms, y of n minus 1, y of n minus 2, we'll do the same thing on the other side. Take the output y of n and delay it however many terms we need. Multiply it by its, notice the opposite, the negative. Negative because typically we would write these on the other side of the equation with the y's. And add those up. And this same generic form would implement any difference equation. Yeah.
Is there any specific reason why the a coefficients are designated negative, or is that just a consequence of what it's actually doing in this case?
Well, again, when we do it the typical way that we would did it in 228, put all the y terms on one side, all the x terms on the other. When we bring these y terms to the opposite side, they get positive exponents, or positive coefficients. So that's really the standard form. And this is the implementation version of that. And this is one of actually several different actual implementation structures that can be used to make any digital filter. This happens to be one that's so closely tied to the difference equation, we call it a direct form. Called a direct form because every one of the coefficients, b1, b2, a1, show up in this diagram. So and we can literally term by term find the term in the difference equation, find the blocks of hardware that implement those particular terms. So there's no additional, no simplifying, no rearranging, just explicitly implementing the difference equation exactly as it's written. Now you go on to take 419, we'll show you some different ways to simplify that or other alternative ways to implement it that are way more efficient, but this is the most basic implementation. Okay. Another difference with continuous time systems, we talked about the filter or the system order in continuous time systems. What determined the order of the system? What made it a second order, third order? What was the determinant there? Remember? What's that? The highest power of x or y. Your x, derivative, y, highest order derivative of the y side. Highest y derivative gave us the filter order. In discrete time systems, the highest delay in y gives me the filter order. So if I have an x, if I have a y of n minus 2 term in my difference equation, it's a second order system. So it's the highest delay term on the y side that gives me the order. And if I throw away, have none of that y term in my equation, I just have y of n in terms of x of n and its delays. This is a non-recursive system, no feedback. And we would call that a zero-order system, which weren't terribly interesting in continuous time systems. Here, though, they create a whole class of systems, discrete time systems and filters that actually are extremely useful and have some extremely wonderful properties. So we'll be spending a lot of time distinguishing the characteristics of non-recursive systems. So we have, well, we've got difference equations, we've got input-output responses, we've got block diagrams. In the future, we're going to come up with some more unit sample responses will be the way we'll put some discipline behind this characterizing responsive systems. Now give rise to our convolution. And then we're going to do all the transform domain stuff we did in 228. We'll pick up the whole problem, move it into some other weird domain. And we'll talk about poles and zeros and transfer functions and frequency responses, frequency spectra, all that stuff's coming back. So, and all those tie back to some of these starting points, starting with a difference equation, starting with a diagram, or starting with some kind of response that we've characterized. So we have ways to describe system, and associated with each of those is a different technique for doing system analysis, where again, when I say system analysis, it usually boils down to you describe the system for me, mathematically, or with one of these descriptions. You give me an input signal, x of n. You give me some initial conditions, what's happening before x of n came in. And then I got to tell you, okay, that signal put in that system with those initial conditions are going to produce this signal. What comes out? What's y of n given that particular input, that particular system, that particular set of initial conditions? And in the time domain, we're going to do that by two key methods. We're going to do that, well, actually 2.5. We're going to do it running the difference equation, first brute force, sample by sample, a method called recursion. Then we'll do it analytically by solving the differential equation, use difference equation, excuse me. And ultimately then we'll come back to establishing the idea of convolution and how that works in discrete time systems using the unit sample response as our surrogate for the impulse response in discrete time systems. That's the next place, that's our next thing to conquer, how to do these things. Well, we'll do this one today, we'll learn that. Before we get into these two, we're going to have to narrow down what's the field of different systems that we can deal with. And so then we'll talk about system classification today and how, which ones we can operate on. Y of n is 3x of n plus 2x of n minus 1 minus a half y of n minus 1. And if we want to draw a diagram, we'll take x of n, we'll have to multiply it by 3. We'll need x of n minus 1, so we'll have to have a delay unit out here. And then multiply it by 2, it looks like. And add those together. Then we'll also have to steal y of n to make y of n minus 1. Give it a gain of minus 1/2. And that so we have a difference equation, we have a block diagram. Both. And if this was actually a system we want to implement, we could build this in digital hardware. You could describe Well, I got 1, 2, 3 fundamental building blocks. So maybe you could even do this. Maybe you could, with Verilog, construct digital components in a hierarchical design, a delay unit, multipliers, adders, and we could piece this together and make digital hardware that would chunk through this. Or I could program a computer to implement that difference equation. Take 3x sub n, take 3 times the net sample coming in, add it to 2 times the previous sample, multiply the previous output by that. Oh, so I've got to grab onto the x of n values and hold them in memory somewhere, so I remember them the next time around. Same thing for y of n, I've got to hold it in memory for at least one step so I can use it next time around. So a little bit of memory, a couple of variables, and a couple of equations, you can implement a difference equation in the computer. So let's do that. Let's be like the computer. Let's figure out what is the output going to be for a particular input signal. And to do that, we use what we call a recursion table. I'm going to have to lose my pretty diagram here. And so in this, we kind of do almost like in a spreadsheet. We keep track of, for each time index, and we're assuming we're going to put in a new signal starting at index n equals 0. And then I'm going to put a new signal in here and compute, based on that new signal, what's going to come out of the system. How we use this table, well, first we have a row for every time index. We have a column for each signal that we have to keep track of. And so just to keep track of where we are, what I'll write in here is the value of x at this index. So x at -1 is that. X at index n equals 0 will be the value I put here, and so on. I'll put in whatever signal I'm putting into my system, x of n, I'll put those values in here. I'm going to need x of n minus 1 to compute in my difference equation. And so I'm going to put the values of a delayed version of that signal in here. And so if n equals 0, I put x of 0 here. At n equals 0, I put x of minus 1 in here. Right? Shifted it all down one. And I'm going to compute at n equals 0, I'm going to compute y of 0. If I'm keeping track of y of n minus 1, again, I'm going to be one index different from that. So these are the values I'll put in each of these places. Do is start off with, what was my input? What is my input signal? What signal am I applying to the system? Well, here's the signal we're going to, if I can draw straight. This one is 0, 0, 0, 0, 0. Then 3 2s, like a square pulse. And then a bunch of zeros after that. So I'll write those values in here. X of 0 is 2, x of 1 is 2, x of 2 is 2, all the rest are zeros before and after. So that's the signal I'm putting into my system. And I want to know what comes out. Where this system is described by this difference equation. So all I need to do is, for every index row, compute the value of this difference equation using all the appropriate values in each of those row positions, in that same row position. All right. So for my x of n minus 1, well, I've got all the values of x of n, so I just need to copy them down. This 0 goes over here now, this 2 goes down here, and so on and so on. It's shifted down by 1. Everybody okay with that? Makes sense. I'm going to do the same thing on this y of n minus 1 term, but first I need some y of n's. All right? And so I'll go across the top to find y at minus 1. I'm going to take 3 times this x of n, add it to 2 times this x of n minus 1, take off half of this y of n minus 2 minus 1, and y minus, I don't have anything there. So here's where I need an initial condition to get started. I'm putting in a new signal starting at n equals 0, so the initial condition I need you to tell me is, what is this value? What is y of minus 1? So I'm going to need that to compute that output at n equals 0. So you got to tell me that. Now, what order is my system? Y of n minus 1. Just like continuous time, first order system, I need one initial condition. The first initial condition is y minus 1. If you have a second order system, you get two initial conditions, y of minus 1, y of minus 2. So we get previous samples, not derivatives, not weird things like that. We get just sample values for initial conditions. Okay, now that I know this, I know what to fill in here. Y of minus 1 is 0. Now, at index n equals 0, I have all the information I need to compute what is the output at time n equals 0. And so let's keep track of what we compute for the outputs. We were told y of minus 1 is 0. What's going on back here, I have no idea. But now I can compute y at n equals 1. We can get this first value, what comes out when this first 2 comes in. And for that, we'll take our difference equation. We'll take 3 times x of n plus 2 times x of n minus 1 minus 1/2 times y minus 1. 6 plus 0, we get 6. Whoops, one place. Over here. And n equals 0, we get a 6. See how we did that? Where the difference equation, the coefficients, multiply them by the value of each of these rows, each of these columns, and add them up. Then this y of 0 comes over here to get me ready to be my y of n minus 1 for the next index. And here I compute y of 1 is 3 times 2 plus 2 times 2 minus 1/2 times 6. Means 7. And that becomes my y of n minus 1 in the next term. And we multiply 3 times 2 plus 2 times 2 minus 1/2 times 7. And that gives me 6.5. Here at n equals 2. So you can finish filling in the rest of the table yourself by that same, just chunking through that same way. We've gotten 3/4, then minus 3/8, and plus 3/16, and minus 3/32. Keeps going on like that. Plus 3/64, minus 328, boom, 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 boom. So I put in a square pulse, and I got a response. response here. Got the response. Whoa. And it's gonna just keep feeding back that output. We're gonna always have a term here. It's gonna keep getting multiplied by a half and a minus. So every time it gets half as big, and then the minus sign just makes it oscillate back and forth, positive, negative, positive, negative, positive, negative, positive. And it keeps doing that forever. It never gets to zero. The transient response never dies out. Transient response is infinitely long. That doesn't sound good. Well, that's just the nature of that particular signal, or that particular system. Everybody see how to do that? That's a recursion table. You could probably think about, hey, I could put that, I could program that in Excel. It kind of mimics exactly what how a computer's going to do it. Take a new sample in, it's going to run through the difference equation, throw out a new output. Keep track of the x and y's it needs for the next time around, store those away, and we'll get the next value. Grab out all the previous stuff it needed from the difference equation, spit out a new output, just keep doing that, just keep chunking, just keep chunking. So the recursion table will tell us exactly what the numeric values will do. What it doesn't give us is an analytical answer. We'd have to try to conceive of, could I write an equation for what this response looks like? That'd be a little hard in this case. The other technique, solving the difference equation, convolution, those will give us analytical answers. Actually, convolution gave us both numeric or analytical answers. Okay, so we're going to describe our discrete time systems output in terms as functions of the input signal, and maybe delayed versions of the input, probably delayed versions of the output. That's going to give us our input-output connection. Now, so that we have a description we can use to do system analysis on, but some of these system analysis techniques require that we have particular kinds of systems. And so in 10 minutes or less, let's see if we can review system classification. It goes very similarly to how it did in 228, same terminology, just adapted to discrete time systems. So, roll up your sleeves, hang on your hat. You've done this all before, so we're going to do it quickly. Is it recursive or non-recursive? That's kind of new. Is it static or dynamic? Oh, you remember that. Linear or nonlinear, the big one. Time invariant or time varying? Now we'll call it shift invariant and shift varying. Is it causal or non-causal? That's back to course stable and unstable. All right. Let's talk about recursive. That's kind of the new one. We already looked at that. Recursive means it's got feedback. It doesn't have feedback if the output term y of n is not brought back into computation. If there's no y of n minus something terms in there, it's non-recursive. Another name for that would be feed-forward. Take the input, maybe delay version of the input, do some computation on it, spit out an output. Just piece of k's and x terms. As soon as I take that y of n, feed it back into the computation, then it's recursive. I'm generally going to do that through some kind of delay or number of delays. So recursion, think feedback. Non-recursive, no feedback. Static and dynamic. What did static mean before? Back in 228. Meant boring. Meant not terribly useful. It meant uninteresting. In discrete time systems, you've seen static versus dynamic very clearly parsed for you. CP133, you learned about combinatorial logic and state machines, right? Combinatorial logic, I can write a Boolean algebra expression or something. You give me the current inputs, all the current inputs, I'll tell you what comes out. And that's all I need to know. What are the inputs right now? I can tell you the output right now. Not so state machines. State machines, what the output was at any given moment didn't just depend on what the inputs were, but what was going on beforehand. They had memory. They had flip-flops. They had registers for keeping old information. So history was able to come in. So static systems are called instantaneous systems, meaning if I'm computing the present output, you only have to tell me the present value of the inputs. I don't need to know about the past. I definitely don't need to know about the future. Here's an example of a static difference equation. It looks like a linear system, but it's not actually. But to compute y at any moment n, all I need to know is x at that same moment. There's no x of n minus anything, no x of n plus anything, no time index changes. So all the x of n and y of n terms have to have the same time index arguments. That means you're not reliant on previous information, so there are no memory elements in a static system. No registers, there's no delay units, nothing that looks like memory. So that means there's got to be no delays or advances in the difference equation. If it's dynamic, you could have y in terms of x of n, could be future x of n's, could be previous x of n's or previous outputs. To compute the index, what's going on at this particular index, I need information from some other time, some other index in front of me or behind me. As soon as I need a different time, it's a dynamic system, implying there's got to be some memory. So I need previous or future values of x of n or y of n. So that's kind of easy, static, dynamic, and most of our systems are going to be dynamic. Linearity is the big one. And linearity is, again, broken up into two pieces, just like it was before. Additivity and homogeneity, which together give me linearity. Here's how that picture goes. Homogeneity means put in a signal x1 into my system and see what comes out. We'll call it y1. Then if I put in a different signal that happens to be scaled by some number a, put that in my system, what comes out better look like y1 scaled by the same number. So scaling the input produces the same, underlying same, scaling of the output. A has to be a numeric scalar constant. Can't be a function of x, y, n, it's just a number. It's allowed to be real, imaginary, or complex, it's still just a number, it's all a scale factor. If I scale the input, I get exactly the same scaling on the output. I need that for linearity. I need that for convolution. I need that for my transforms to work. Okay. The other piece we need is additivity. Additivity says, again, put in some x1 signal, get out something called y1. Put in a different signal, call it x2, get out a different signal called y2. So we know how the system works in those conditions. If I then choose to put in a signal that happens to be the sum of these two, called x3, that's the sum of these two. Put that in my system, what better comes out better be exactly y1 plus y2. If I added things on the input, I better add the responses on the output. The responses are additive, without any additional scaling, shifting, or anything else. So summing two inputs produces the sum of their individual responses. This is absolutely essential for linearity. Again, mimics completely the same definitions we had in continuous time systems. Just now we have samplers. Okay, together they make linearity, which gives us superposition, which says you put in x1, you get in y1, you put in x2, you get y2. If I scale x1, I get scaled y2. If I add it to a differently scaled x2, I get a differently scaled y2. They all work together, they all intermix. You can scale them, you can add them, and the output responses suffer the exact same. By the same amounts, still add, nothing's changed. And that's the whole, we have a truly linear system. Right? So how do we spot that looking at a different? Nonlinear difference equations have either a constant additive term, that actually makes it nonlinear, it violates those principles if it has an additive term, and products of inputs with themselves, inputs with outputs, any combination, cross combination of input and output products give me nonlinear. This one's obvious. A squared is not a linear thing. But even these intermixed products, all we can have are x of n's, y of n's, and numeric coefficients. No functions of x or y in front of our x and y's. Okay, that's the number one big thing we need, linearity. Time invariance is the other, which in time we don't have time anymore, we have samples. So we call it shift invariance. But it's conceptually the same as time invariance. If I put a signal x1 in and I get out a y1, if I put in another signal that happens to be just x1 delayed by a couple of samples, put that in my system, what better come out is y1 delayed by exactly the same amount. So if I shifted x1 by 3, y1 better come out shifted by 3. Shift invariant, the shift that happens on the input, I get exactly the same shift on the output. So a way of saying my system doesn't compress or expand time. It keeps everything in lockstep. I delayed it on the input, I delayed it on the output. Another way of saying that conceptually, shift invariance implies that a sample shift on the input produces the identical sample shift on the output. It also means that the system response can't change with sample position, which is also like saying it can't change in time. So I take a signal and I measure its response. I put that same signal in a day from now, I better get the same output response, or else I have violated shift invariance. And so the system has to be time stable, or in this case, shift stable. How do you check that out of the difference equation? Well, it violates it. It's a time varying. If your coefficients in front of your x's and y's are functions of n, that's a dead giveaway. And it also turns out if you have time scaled arguments, that will also imply my system's doing time scaling. It's no longer shift invariant. So no expansion. Give us a linear shift invariant system. We'll take linear time invariant. We're going to call these LTI systems just like we did in 228. Those are the kind that all of our good things are going to work. Convolution works on, transforms work on, but they all rely on having a linear shift invariant system. And if they are both, then I have just y terms, x terms, and all of the leading numbers or things that go with them are numeric constants. So we have a linear constant coefficient difference equation. Causality. System can't anticipate. Kind of like dynamic. All I need to know is the input right now or in the past. I can't need any future information because that's anticipated. Causal systems don't use future values of x. So that means my difference equation, we don't have any x of n plus things because those haven't arrived yet. Plus things, x of n plus 1, x of n plus 5, if I'm describing my output of y of n. That means future information that hasn't arrived yet. And again, if you have compression or expansion, that violates causality too. you got x of y equals x of 3n, well, take n equals 3. Then y of 3 needs x of 9. It hasn't come yet. There's still 6 samples waiting for that. And come the other time, n over 2 messes you up in the negative direction. Need to let you go. Looks like we're past time. So that's the whole story. You now can do that. For homework, there's some